Okay, here's our first review video for the upcoming exam, and in this first video I'll start out by showing you how you can identify what kind of conic section an equation represents without doing any calculations. And the first thing you should notice here is that I set these equations up so that all the terms are positive, which is exactly how your exam questions will be arranged. So, for instance, this first one, I believe when I first found it, it was 4x squared minus 25y squared, but I want all the terms to be positive, and there's a reason for that we'll get to in a second. And now, given this form, with everything positive, if one of these equations has one of its quadratic terms on one side and one on the other, that equation will describe an hyperbola. This is because when we collect all variable terms on one side, one of the quadratic terms is going to be negative, which will correspond to a negative fraction when we're done simplifying. And since this is the case in this first equation, we know it describes an hyperbola before we do anything else. Now in the next equation, both quadratic terms are on the same side of the equation and they have the same coefficient. This tells us that the equation describes a circle. Now that coefficient happens to be 1 in this case, but that's not always true for circles. It's the equality of the coefficients that matters. Now in the next equation, only one of the variables has a quadratic term, and so that tells us that the equation describes a parabola. And finally, in the last equation here, both positive quadratic terms are on the same side of the equation, which tells us that the equation describes an ellipse. And so here we see the equations simplified, and so confirming that the indications that I just described are correct. So let's review some of the characteristics of these equations and their figures. First, a circle, even though it's not listed first. A circle has, the simplified equation has no fractions. There are no fractions in the simplified version of the circle. The center for the circle and for any of these figures is opposite sign, and that means that here, for instance, the center of this circle is -3 and +1. The center of this hyperbola is +5 and +3. And the center of this ellipse is +3, -1. And of course, for the parabola, here, it's not the center that's indicated, it's the vertex, as I have noted here. Now, as for the parabola, when the quadratic term is x squared, then the parabola will open up or down. Down if this 4a, which is what this is negative. Up if this is positive. When the quadratic term is y, so y squared, that indicates that the parabola opens left or right. Right when this value is positive, left when this value is negative. And don't forget, a is a distance, so it's always positive. It's the distance from the vertex to the focus, which is equal to the distance from the vertex to the directrix, and I will show you the figure of a parabola here in a second, and you'll remember it very well, I'm sure. And then in an ellipse and a hyperbola, both variables are squared. There's a there's a perfect square for both the x and the y terms. For an ellipse, there's a plus between these two fractions. For an hyperbola, there is a minus between these two fractions. And now let's take a look at an ellipse and the relationship between the A, the B, and the C. Now these are not labeled, but the coordinate, the x-coordinate of this point is our A, and it's the distance from the center to the vertex. These are vertices. This is a vertex, that's a vertex, and the A, obviously, the A is always larger than the C. It's always going to be larger than the C. And it is usually, and the C is usually larger than the B, but that is not absolutely necessarily the case. And so I'll show you that. I'll just bring these foci closer and closer, and you can see we still have an ellipse, but the B, the length of the semi-minor axis, is less than the C here. I think probably for your questions, the C is going to be bigger than the B. Now when, and the bigger length, when it's corresponds, when it's underneath the x squared fraction, that's going to correspond to an ellipse that opens, or not opens, but is aligned oblong left and right. It's wider than it is tall. When the distance, when the semi-major axis, or rather the major axis, is vertical, then that's going to correspond to a larger number underneath the y squared term. Okay, here's the table of equations that refers to what I was talking about just a minute ago, with the larger number being under the quadratic term that corresponds to the direction that the ellipse runs. So under x squared means left and right, parallel to the x-axis, and under the y squared term means up and down, parallel to the y-axis. And I think people have a reasonably good handle on that. You may also want to take a look in your text and remind yourself what these equations mean. Y equal k being a horizontal line, and x equals h being a vertical line. What I think is probably a little more confusing is the equations of an hyperbola. And I thought of this way to sort of simplify how you look at those, how you might remember those, and that's with this. I'm using this color coding and this way of looking at it. The hyperbola is going to have its transverse axis parallel to the first variable in the equation. So ellipses always have x squared first, and a squared will be under one term or another. Hyperbolae always have the variable first that corresponds to the transverse axis parallel to that variable's axis. So remember, the transverse axis is the axis that runs through the two foci, the two vertices, and the center. And so when the first variable in the equation of the ellipse is the x, it's the x quadratic term, then the ellipse is going to look like this, with its transverse axis going left and right, and the hyperbola opening left and right. Now when the first variable in the equation is the y, or the y terms rather, then the transverse axis is vertical, it's parallel to the y-axis, and the hyperbolae, the wings of the hyperbolae open up and down. And then one other thing to remember about hyperbolae and their figures are that when this axis, when the transverse axis is parallel to the x-axis, the slopes of your asymptotes are going to be plus or minus b over a. And I've coded this blue, and if you want to remember b for blue over a, parallel to the x-axis, blue, and when the parallel to the y-axis means that the slopes of the asymptotes are a over b, a over b. And to plot those asymptotes, you don't have to simplify these equations here. All you have to do is start at the center and use the slope. Count b units up, and then a units over, b units up, a units over, b units up, a units over, and to get the, and then that'll give you the positive slope asymptote. To get the negative, you just count b units up, a units to the left, b units up, a units to the left, and that will give you the negative slope asymptote when we're parallel, when the transverse axis is parallel to the x-axis. Of course, when parallel to the y-axis, you count a units, you start at the center and you count a units up and b units to the right, a units up, b units to the right for the positive slope, and for the negative slope it's a units up and b units left, a units up and b units left. Right, left. Correct. Left. Okay. And let's see, the last thing I wanted to show you was I wanted to go through completing the square on one side of the equation. This is the first equation that I showed you when I started this video. It's an hyperbola, as you recall. And so the first step in simplifying this equation is to subtract the 25y squared and the 24x from both sides of the equation. So I've got all my variables on one side of the equation, typically the left, and I have the constant term, the number, on the right. It doesn't have to stay on the right, but it's already there, so I'm just going to leave it. It's a little more convenient. And then I look at the x terms, the 4x squared, the negative 24x, and I factor out the 4. You have to factor out the coefficient of that quadratic term. So I factor out the 4, and I leave inside the parentheses x squared minus 6x. Now, half of minus 6, half of negative 6 is negative 3. So that's going to go here, and so negative 3 squared is 9, positive 9, so that's what's going to go here. You're going to add a 9 here. We actually added to this side of the equation, we actually added 4 times 9, positive 36, so we had to subtract 36 to compensate. Over here, we factor out negative 25. If you factor negative 25 out of positive 250, that leaves negative 10. So inside our parentheses we have y squared minus 10. Half of negative 10 is negative 5, so that's what goes here to complete our square. And then negative 5 squared is positive 25, so that's what we add here. Well, what we actually added to this side of the equation is negative 25 times positive 25, so that's negative 625. So we add a positive 625 to this side of the equation to compensate for that. In the next step, I collected the factors to write the squares, and then I just put the negative 36 over here next to the 625. I put them in the same neighborhood. When you subtract 36 from 625, you get 589, and then it's the steps not shown here, but I subtract 589 from both sides, and that leaves negative 100 on this side of the equation, and these two squares on the left. Now I don't want negative 100 on this side of the equation, I want 1. And so I multiply by the reciprocal of negative 100, which is negative 1 over 100. And when you multiply those two together, you get 1. When you multiply them on this side, the negative 1 over 100 times the 4 times the x minus 3 squared makes this term negative. The 4 divided by 100 is 25. And because it's negative, it's going to be the second term in the equation. When you multiply the negative 1 over 100 times the negative 25, you get a positive 4. So that changes this term to positive, and that's why it goes first. And we saw that that means that if we were to sketch this hyperbola, we would have a transverse axis parallel to the y-axis. Okay.